How exactly does SpaceX build a Super Heavy booster? Super Heavy, Starship's first stage, is the most powerful rocket stage ever built, and it has a big role to play. Not only does it have to loft 1,300 tons of Starship propellant and payload, but it needs to fly back, land, and then be reflown. So it must be pretty complex, right? We'll take you through the build and test process of the Super Heavy booster, everything needed to get it ready for launch.
This video is sponsored by Blinkist.
The assembly process of Super Heavy begins with the delivery of raw materials. Just like with Starship, 11-ton coils of 304L stainless steel are delivered to the production site, and these will become the walls of the tanks. This steel is 4mm thick enough to support the weight of the vehicle and the tank pressure, while thin enough to not be too heavy. SpaceX has been experimenting with thinner tank walls for Starship, but no changes to Super Heavy have been made so far. The rolls of steel are used to make the 9-meter diameter rings that form the tanks. To do this, the coils are placed into a jig and partially unrolled until just over 28 meters of steel is unfurled. The exposed section is then cut and welded into a complete ring, and the process is repeated again 36 more times. And weirdly enough, Super Heavy does not actually use the same size rings for all of its construction. 33 of the rings are the standard 1.8 meter height, while the 4 rings making up its aft sleeve section, the part where the engines are integrated, stand at a shorter 1.4 meters in height. 2 smaller diameter 1 meter tall rings and one 1.7 meter tall ring are also cut to form the liquid oxygen header tank for the booster. On launch day, this tank will hold a small amount of liquid oxygen specifically for the landing burn, as the liquid oxygen inside the main tank may be sloshing about and not covering the engine inlets. If an engine was to suck in gas instead of liquid, you wouldn't have an engine anymore, let's just say. So, once you have your ring sections made, I assume you're following along at home, you want to move on to making the tank domes. Each dome, or bulkhead, is made of 2 different types of steel pieces, though SpaceX is experimenting with flatter elliptical domes made with only one type of steel piece. SpaceX receives stamped dome panels and welds them together to create the 2 parts of a dome, the knuckle and the frustum. These are then joined together as well, although a large opening remains on the top. For the booster's forward dome, a cap is placed on the opening to seal it. The opening on the common dome is left in place. The methane transfer tube assembly will later be slotted into that area. The aft bulkhead, however, is of a slightly different design. In order to fit the large engine plate, this dome is made shorter and heavily reinforced. 20 holes for oxygen and 20 holes for methane are cut along the perimeter of the dome knuckle to feed the outer 20 Raptor engines. This whole assembly will need to withstand 7,500 tons of thrust from the 33 engines, so it needs to be strong. The engine plate itself is made from a large flat piece of machined steel and placed in the wider opening of the aft bulkhead. This supports the inner set of 13 gimbaling Raptor engines. And now we have all the big pieces of our Super Heavy booster. Let's put them together. SpaceX robotically welds rings into stacks of 3 or 4 for Super Heavy. These rings are stacked to allow SpaceX to pre-assemble and work on parts of the vehicle on the ground, which is much easier, safer and quicker than if they were already stacked high up on the vehicle. Whether a ring stack has 3 or 4 rings depends on where it will be located on the booster and what components are installed on it. Portions of stringers are now added to these stacks. These give additional strength and rigidity to the booster. The remaining stringers will be added over the weld lines between stacks during final booster stacking, but we'll get to that in a bit.
Ryan, you and I keep really busy with live streams, editing, and of course chasing rockets, but it really limits my time to read and learn. That's where this video's sponsor, Blinkist, comes in. Blinkist allows you to take away the main ideas from over 5,500 nonfiction books and podcasts in just 15 minutes. With 27 different categories to choose from, Blinkist can help you discover new perspectives and broaden your horizons in all kinds of different topics. I travel a lot to cover rocket launches, and now I can learn a lot in a fun way without ever taking my eyes off the road or the rocket. There's a fantastic blink called Shoot for the Moon, and it's not entirely what you think. It takes a look at the smart decisions and life choices made by Apollo flight controllers and looks at how we can apply those to our everyday lives, and probably to the workers at Starbase as well. I love the quote from Jerry Bostock on Apollo 11, quote, "Just because you can't do everything you want to do doesn't mean you should give up and do nothing." And now, Blinkist has a brand new feature called Blinkist Spaces. This feature allows you to create a space with friends or family, where you can recommend titles to each other. All members of a shared space can access all titles in that space, with or without a Blinkist Premium subscription. To get started, visit Blinkist.com/NSFFriends, where you can get a free 7-day trial and 25% off Blinkist Premium. Thanks to Blinkist for sponsoring this video. Back to you, Ryan.
The ring stacks are now sleeved over the domes, integrating the two together. The forward dome is sleeved by a 3-ring section, while the common dome gets sleeved by a 4-ring section. The aft dome gets sleeved in its special 4 short ring stack that we mentioned earlier. The tank vents and some miscellaneous external piping are added to the stacks here for tank pressurization and other purposes. Finally, the COPVs, or composite overwrapped pressure vessels, are added around the vehicle. These contain high pressure gas to help restart some of the Raptor engines during flight for the boost back and landing burns. In addition, the completed header tank is attached to the middle of the engine plate alongside this chaotic looking object. This critical manifold will feed the liquid methane to the 33 Raptor engines on the base of the booster. Once all 10 ring sections are ready, we can begin stacking. So get out your bridge crane and your welding robots. The 2 propellant tanks built from separate ring sections are assembled individually. Again, this allows SpaceX to work on 2 parts of the vehicle at once and at much lower heights than if they stacked it all in one go. Funny enough, the tanks are actually stacked top down. So the forward dome, the topmost part of the methane tank, is joined with the section below it first, and so on. Likewise, the liquid oxygen tank is stacked starting with the common bulkhead section before adding the sections below that. As we mentioned before, the final stringers are added here as well. They go over the weld lines between ring stacks, thus completing the internal structure of the vehicle. The methane transfer tube is then installed into the common bulkhead and liquid oxygen tank. Also, the steel grid fins, which steer the booster as it returns to land, are attached to the forward dome section. The oxygen tank is now joined with the stacked aft section, and the methane tank is stacked on top of that. Finally, the chines are added, which protect the COPVs from aerodynamic effects and provide some lift to control the booster as it returns, basically acting as stubby wings. And finally, we have a fully stacked booster. Let's get into some initial testing, shall we? SpaceX now rolls out the booster to the launch site for cryogenic proof testing. However, this testing may be shifting over to the new test area at the former Massey's gun range site. Cryogenic proof testing, which sees both tanks filled with non-flammable liquid nitrogen, ensures that the booster has no leaks and can reliably hold cryogenic liquids inside. I'll also note, however, that we've seen indications of liquid oxygen being mixed into these cryogenic tests, especially with the new Massey's site beginning to come online. It's important to note that the Raptor engines usually are not installed at this point. If your vehicle fails cryogenic testing, you don't want millions of dollars worth of Raptors being damaged as well. This test is pretty important as you don't want liquid methane to leak from a vehicle on the pad. We all know what happened with SN4 and then SN10. With the booster now safely at its test site and hooked up to the liquid nitrogen system, both tanks of the vehicle are filled and pressurized. If all goes well, the liquid nitrogen is then drained and the booster is transported back to the production site. Now, all of the remaining work ahead of the flight is performed. The booster's Raptor engines and engine shielding are installed at this time. And if you want to learn more about the Raptor engines and their journey from factory to flight, stay tuned for a future video. You know how to stick around. Not only will the shielding protect the Raptor engines during re-entry, but if an engine fails during flight, like multiple engines did on the first Starship integrated flight, it will attempt to contain any debris so adjacent engines are not damaged. Once the Raptors are installed and plumbed in, the booster makes what should be its final trip to the launch site. Atop the orbital launch mount, the booster then performs one or more static fire tests of its Raptor engines. These tests ensure that every system on the booster is working properly ahead of launch day. Around this time, SpaceX may opt to perform full stack testing. This is when they stack a Starship atop the booster and can perform a variety of tests. These may include a wet dress rehearsal where both stages are fully loaded with methane and oxygen, simulating a launch countdown. If you'd like to perform some full-stack testing yourself, head to shop.nasaspaceflight.com and pre-order our full-stack Starship plushie set. You can integrate both the ship and the booster together to make your very own Starship launcher. If all of this testing goes well and inspections show no issues, then we come to the moment you've all been waiting for. The vehicle is cleared for flight. On launch day, the fully stacked Starship launch vehicle is loaded with propellants. As the minutes count down, all systems on board the ship and booster are checked out. Just seconds before liftoff, the 33 Raptor engines at the base of the rocket ignite and ramp up to full power. And then it finally happens. After months of assembly, testing, inspections and hardware installation, the Super Heavy booster lifts off the pad, carrying Starship and its payload to orbit. The vehicle races away from the tower and starts pitching downrange. Super Heavy's Raptors will burn for around 2 minutes before shutting down. The booster will then loosen its grasp on Starship, which will ignite its own 6 Raptors to continue to orbit. Super Heavy then flips around, igniting a few of its own Raptors to return to the launch site. Interestingly, the booster doesn't need to perform an entry burn like Falcon 9. Since steel melts at a much higher temperature than aluminium, the booster simply punches through re-entry. Just seconds before it would hit the ground, the booster again reignites a small group of engines to slow itself down. It is then caught by the chopsticks on the launch tower, ready to fly again. Now we have our Super Heavy booster, we of course need a ship to fly on top of it, so if you'd like to learn how to build one of those, check out our previous video called How to Build a Starship.
Don't forget to visit Blinkist.com/NSFFriends to get a free 7-day trial and 25% off Blinkist Premium.
I hope this video helped you to understand the process of building, testing and eventually flying a Super Heavy booster much more, because it's quite a difficult process to understand. Thanks for watching and goodbye.